My name is Dennis. I am an engineer at Bolt, and I'm working on our data science platform. Super excited to be here and to meet Kyiv's data science community. You're doing a really great job here, and it's my honor and pleasure to be here. I'm going to talk about something really, really practical. So I'm not going to talk about any particular model or any particular technology, but I'm going to talk about how to make those things that you guys develop here to run successfully and improve lives of customers, clients, and improve your product. Well, at the first presentation, there was a question, who of you is in data science? Now I'm going to ask the question, who of you have ever deployed model to production with their hands? Awesome. Take a look at that. I mean, left side, I mean, right side, what are you doing here? Like, left side is deploying all the models. Good job, guys. So you guys come and talk to them afterwards and learn what they're doing. That's pretty exciting. I'm going to talk a bit about Bolt and why our experience can be highly relevant to many of you in different companies, and what we have learned in our journey of scaling data science and developing this function from scratch in the company. Have you used Bolt here in Kyiv? Yeah, all right. So people have used it. You also have a coupon somewhere in your welcome pack, so take the ride home. Bolt is a leading transportation platform in Europe and Africa. We are not only doing taxi rides, we also do scooters. During the last 12 months, we've launched scooters. We have motorcycles running in Africa, and also we launched food delivery last month, and we are growing really, really fast. We are the fastest growing ride-hailing company in the world, and we are in top 3 fastest growing European companies. So in the last few years, we have grown to 25 million of riders, to more than 100 cities and more than 30 countries. And also, our team has grown significantly. So why am I telling you all of that? Why does some business success has to do with data science, and why you guys should spend your time listening to me here? From the, oh my God, what's happening? Is it all right? No epilepsy here, please? So I hope you can survive it with those slides. Bolt has been a data-driven company from the very beginning, from starting really small in Tallinn 6 years ago. And our data science is actually quite young. Less than 2 years ago, there was no data science. And since then, we have grown to support many of the products and many of the features with machine learning algorithms. So what are the challenges that can be solved? I mean, ordering a car, it's super easy, right? Where can you apply machine learning there? Is it? Oh, yay. No. It's going the wrong way. So we are competing in really, really large market across people, companies that have orders of magnitude larger engineering teams and that have much more funding than we do. And we're able to compete with them successfully and fight them off in many, many markets. So to do that, we need to grow sustainably and invest money in the place where it matters. This is one of the directions for data science. Another one is pricing. We are operating in real time, in real cities, where real drivers leave their home, sit in the car, and they make their living. So we need to choose the optimal price to balance the demand and supply in the cities in real time. And also we do build our own maps infrastructure for routing and predicting ETAs, estimated time of arrival. We have to fight off the bad guys and do many more things. And all of that is done by an incredibly small team. We can try to change the frequency, no? Just 2 per minute? We can bring another. Who has better laptop than I do? There is a link on Google Slides. I challenge you to find a better laptop. Who is annoyed by that? Yeah. Bring your laptop. Yay. OK, I can continue without slides while we don't have them. And also, big part of the challenge is that we don't only have many different models across a variety of domains, but we are super localized, which means that if I have model of type A, it means that for every city, we have this model. We have to train model for every city separately, deploy it, serve it, retrain it, and be able to monitor it and understand the performance of the model. There are many, many challenges that are coming with that. And now is the time where I do need slides to explain what I want to explain. But I guess you guys can bear with me for some more time. So there are many, many interesting things that we are solving, and our data team is really, really small. So I think our experience is highly relevant to those of you who are starting your journey of building up data science function in your company. And the key message to take home would be which projects and which technology can you build to make your data scientist more productive. So that's going to be the main thing. So yeah, I see some. It's up. It's up. Cool. Then, so the title of the talk was about scaling data science. So when you tell this phrase, scaling data science, probably each of you has your own opinion or understanding what it means. I'm going to share my own. To me, scaling data science is about improving your ability to learn from the data and improve your product, life of your users, or whatever you care about. Large-scale machine learning is a part of that. Large models, distributed training, high load, all of that is really important. But to scale data science, you don't have to be a large-scale company. And everyone can improve their ability to do data science. Now, let's think about a person joining the field. There are many of you who want to get into data science field here. So you probably think that life is a bit like that. You spend some time on understanding the problem, defining the KPIs you care about. Then you would collect the data, download CSV from Kaggle or whatever, Google Drive, whatever you use. Then you'll probably write some code to parse it, preprocess it, maybe something else. You'd spend a lot of time to actually do the model training, try different things, try ensembles, try hyperparameter tuning, do a lot of feature engineering. And that is really important, and that's what makes your model good. And there will be some integration in the end, probably done by engineers, and that's success. Boom, you are on Hawaii, drinking mojito, earning like 6-figure salary, and life is good. But in reality, data collection part takes much more time. Developing infrastructure takes much more time. Integration is a beast. And you don't get to spend as much time to optimize the model as you want. At least if you're working in a product company like I do. And this slide is based on the information from the Google employees, and Google is not a small startup. And we are a startup at a high growth stage. We are bumping up our team, hiring people, and for us, situation is even more like that. We spend much more time to get the data, much more time to build infrastructure. And these things in the red boxes are the things that data scientists actually care about. The understanding the problem and building up the model is something that you guys have skills in. That's what you're trained to do. That's what you want to do. But from the total time spent by a team to get something ready, that is what it takes. It's really small portion of time. And that can be frustrating. Depending on your size, it might be just one person doing everything. From idea, data collection, pre-processing, building up the model, deploying to production. Or it might be a team. But the proportion will still stay the same. Somebody has to build these things. And I think this is one of the biggest problems that people don't see when they start data science project for the first time or even do their second one. The reality is much harder. Data science is harder than regular software engineering because you have more moving pieces. You don't have only software, you also have the data. And it's becoming more complex. Have you seen those drawing tutorials? Yeah. I also seen them. I tried. I'm not really good at drawing. But when thinking about data science, I think it's something like that. So here you have import keras, and here you have the real world. And in the real world, this probably would look something like that. So here you have this machine learning code that we talk the most about, how to train the model, how to get the best performance, which metric to choose, what to optimize. And sorry for this red square not in a place. I should do something with me after that. But there are many more pieces that should happen so that your model will become part of a successful system that is actually improving somebody's life. We talk about data collection, feature extraction, both for training and inference. Validating the data. You don't want rubbish on input and rubbish on output. Building up things that would allow you to scale your training, to scale the serving infrastructure so that you can actually make predictions in batch or in real time, depending on what do you do. And of course, you want to monitor and know when things go wrong, because things will go wrong. So how do we actually scale data science? How do you scale data science? Of course, you can hire twice as many people. You can hire 10 times more people. Will it give you 10 times better results? I don't know. I'm really skeptical about that. So I'm going to tell you what does it mean to scale data science at Bolt and how do we approach it. To us, in order to scale data science, we need to give the best tools to our people so that they can own and develop their solutions with as least distractions as possible. Which means taking all these components over here that have to be built for every model and making them accessible to everyone who wants to build a model. So on a high level, I'll get a bit deeper. I don't have enough time to talk about all the things that we are building, but from the kind of high-level component perspective, we have something. If it's data science, there should be data somewhere, right? No? Anybody disagree with me? OK, so you're right. If you don't agree, please come later. So there is preprocessing, because if you have several hundred tables in your data warehouse, you cannot just put 500 tables into your model. You probably need to get some features out of that, preprocess it, make analysis simpler. And also there is actually models part. How do you train? How do you deploy model? How do you A/B test them? And how do you scale them when it's needed? And it's all based on the ability to have high-quality data and verify that the data that is input to your system, that it doesn't have bugs, it doesn't have undesired values. An ability for data scientists to actually put their hands on the data, explore it, and try out different things. That is all really important. Let me talk through some of the components, and later, in the end, you'll see why I talk about that. Since quite early in the company life, we've used AWS Redshift as a data warehouse, so the place where we replicate production databases, like MySQL in our case. We replicate data there so that people can run complex analytical queries without DBAs coming and killing us. And as we grow larger, Redshift will become too expensive and too slow. So we are building up our data lake on top of S3. We use Kafka to stream events from DB and microservices with low latency. And we use Elastic and more tools. But from what you can see here, these two things are managed. We don't have to kind of provision machines for that. And these are not. So the preprocessing part. This is something closer to what you guys do. You probably want to extract features, both for training and inference. And for that, we use multiple things. I'll just mention a couple of them. We use Spark. Yeah, who doesn't use Spark if you have a relatively large amount of data? And we use Airflow. Have you used Airflow? OK, oh, somebody. I was afraid that nobody uses it. OK, cool. So we started using it this year, and it helped us a lot to bring the sanity into our pipelines. and make dependencies between different components clearer. And it's proven to be quite valuable to us. And on the model lifecycle, there are many pieces, but I'm just going to bring up 2 of them. Initially, one of the solutions for inference, for serving models, was to compile it to C. And this C function, you can think of, was wrapped as a Node.js package, because our backend is in Node.js. So for our backend services, calling the model would be just call a function from some library. This was nice. It has super low latency. You can get really high throughput in the system. But it lacks flexibility. You cannot install all the libraries. You cannot do complex preprocessing there. So we had to build something that data scientists will have more freedom. And one of the tools that helped us in the beginning, and we still use it, is AWS SageMaker. We don't use all the functionality. It has many, many interesting things. We use it mostly as a serverless way to run a training, or like relatively serverless, and to deploy machines, provision machines that would run our models. Right now, at our scale, it becomes harder to use it, so we have to invest more. But in the beginning, this was a really good tool that gave the power to the hands of data scientists to train, deploy their models to real life. So let me ask you, what is the most important thing in machine learning? What? Data. Data. OK. More specifically, how would you call this data? Label data. Good. What else? What was there? Features. Yes, that was the word I was looking for. Thank you, guys. You led them to the right direction. Yeah. Features is the life and blood of machine learning. You need them for training. You need them for inference. You have to engineer them somehow. And that's kind of really important thing, right? So we've looked at this chart. And it turned out that for us, a lot of time went into actually feature engineering, getting the data out there in production. For some problems, it's easy. If, for example, you have email, spam classificator, the text of the email that comes to you through API is everything you need. You need this text and a model. But if you need to make a prediction in real time, when you open an app, we need to know how much time it will take for a car to get to you. And we may need to know more things. For example, how many rides have you done in the past week, for example? These are the things that you cannot just simply extract from production database. And this part of feature engineering is a complicated thing, and it's becoming harder the larger scale you have. So we saw that the biggest opportunity to cut down time and effort in machine learning project for us was to focus and invest into this part. That's why we decided to build a feature store. The goal of feature store is to be a single place where data scientists can define the features, the code that would extract the features. And if this great feature was developed for one model, and it can be used in another model, we want another model to be easily able to use it. So you don't have to reinvent things twice. That's how we can save a lot of time on feature engineering by our data scientists. And also, for us, really important thing was that if data scientist comes up with a new feature, backend developers don't have to do anything. They don't have to change the code of the service that uses the model. Because we want data scientists to be able to iterate rapidly, try out new things rapidly, and to make innovation faster. So these were the things we really, really wanted to achieve with the feature store. So, do you think that there are many people who talk about machine learning in production? OK, somebody says, OK, somebody nods. You think yes. Somebody thinks who thinks that people don't talk enough about machine learning in production? OK, some of you. I think that you don't often hear at conferences about how people deploy models, how people test them, and what fuck-ups do they have. Maybe it's trade secret how you serve your models, or maybe they're just too ashamed of that. So I think that in most companies, they're just ashamed to share it, because it's done maybe in a really ugly way. I'm gonna take something that I'm ashamed of and walk you through the journey of improving the service, but I'm gonna tell you how it all started. The first version of Feature Store was that simple. So we have Redshift on the left. This is data warehouse. You can run SQL queries on top of that. We had a Node.js service that had a cron job that was running every 24 hours. It was executing a bunch of queries, hard-coded in the code. And it was doing select, feature 1, feature 2, feature 3. And the results were streamed to Redis. Redis is a fast in-memory data store. So that the backend API was able to ask, to say, give me features for user with ID 1, 2, 3. And this would be just a lookup of one key in Redis. Pretty fast operation, super simple. This thing solved many problems already for us. But when it was the first time when a new model appeared, since I joined the company, data scientists said, oh, I need this like 20 features. It took me more than 1 month to get them to production. Yeah, I'm ashamed of that. But it took a lot of time because we hit scalability problems, but most importantly, we hit process problems. The query to compute those features, there were like 4 queries, and they were sent to me via Slack or attached in Jira tickets. Then they changed, and I had to copy these queries into backend repository. Data scientists didn't have access to that repository. I made mistakes. Doing code review was impossible because there was no Git. This query was not anywhere in Git. And there was a lot of back and forth between data scientists, me, and teams who would use it. We needed something better. We wanted to give ability to data scientists to own their features from idea to production. But how do we do that? We hire smart engineers, and we hire smart data scientists. Not every data scientist is a great backend engineer. Not everybody knows the language that we use to develop in our backend. So we decided that we need to give them ability to speak their language. For our data scientists, SQL is their second language. So they speak English, they speak Python, they speak SQL. Probably SQL is third language. So we wanted to give them ability to use the tools that they use in their daily life and to define the features. So here, it's nice, really nicely formatted JSON. This example of simple feature definition. So I would say this is the feature group write count that belongs to rider. And a rider can have multiple of those feature groups that compute one or more features. So who is the owner? This is really important, because otherwise you would say, oh, who have developed this piece of code? There is a query, for example, select user ID, and this user ID would be used to join these features with other features, and count all orders as a write count. Super simple feature, nothing complicated. Group by user ID. Here we define the array of features, and this feature write count has some description, and also array of data quality checks. We didn't have it in the beginning, but we saw that this is really important for data scientists to be able to express their understanding of what values are allowed. Can write count be negative? I mean, unless you can go back in time or something, I don't think it can. So we wanted to give the tools so that data scientists can express in SQL and some simple Boolean predicate whether this feature is correct or not. If it's -1, I don't want this feature to go into production. These kind of things. We added it actually quite recently, and it has proven to save a lot of money on not having big fuck-ups. So this is roughly the way that features are defined. I think this is a really big deal. If you don't, let me convince you. Because now, when data scientists want to add a new feature, they create a pull request to us. I don't know, this is a super big deal to me. They don't send me Slack message. They create a pull request, and they fill this nicely formatted template with all the things. All I have to do is to look over that, approve it, and maybe release the service, and tomorrow it's in production. And this is a big change in the process. and they put the features into production. You can avoid so many mistakes by having something like that. So let me brag a bit how we developed the technical part. I think the biggest change happened here. Instead of just making SQL and putting whatever the SQL returned to Redis directly, we stored a snapshot. So every day when we compute the features for riders, we also store them in data warehouse. So data scientists can go there and see what is the value for every feature. They can do analysis, how the feature has evolved for the user, for example, and whatever things they want to. And it's super useful to find bugs. So, and we also started running data quality checks on this data. This was change number 1. Change number 2, after those 4 queries were implemented, the job became, it took 5 hours to complete. It was like super dead slow. We had to utilize some of the parallelism of Redshift and put it to S3, but this is like a minor technical detail. And then we had a new challenge. I explained to you at first that Feature Store was able to answer the question, give me features for user Dennis. And that's it. But business came with questions. Can we do the reverse problem? Can you give me all the users who have certain features? And we don't know what we want. If you guys know something about SQL databases, usually you would create indexes for the queries that you expect. But in this case, we couldn't expect anything. Whatever business person would enter it, the system should be able to handle it. So we cannot use usual database for that. Data warehouse would be too slow for that. So we had to do something else. We used queues to replicate the stream of features, so batch features and stream features, to Redis that we already had, but also to Elasticsearch. In our use cases, Elasticsearch was able to answer the questions relatively fast. So we utilize its full text search capability for answering random questions. That's it. And it performs relatively well under the current load. So this is the technical thing. And what have we achieved with that? First thing was faster idea to production cycle. Instead of a lot of back and forth communication and depending on the sprints of developers, data scientists were able to publish changes to the feature store code base and have the features ready on the next day. Last week, it took me literally 20 minutes to look at the pull request, deploy it, and next morning, data scientists had their feature that improved some of the metrics and were able to save us money. Reduced job time by 80%. I mean, at usual software engineering conference, I would brag that we reduced storage, we increased throughput, all of that. It's not that important, but it's still important that you think about performance whenever you design a system. I think bigger thing is feature reusability. We have some of the models which are similar in their nature. They want to predict something about user. Will you become active user? Will you churn? Or what different kind of things. And some of the features can be reused. And it's done. This is great. Less time is spent on defining and writing duplicated code to get the same data. People can just start using the feature. Pretty great. Whenever you build a great technology, usually you would see that somebody else start to use them in a way you did not expect. Initially built for machine learning, this tool found a use case for many backend services that wanted to have some aggregated values cached with some periodically. And our fraud prevention teams and many others have been able to utilize this for their benefit and save a lot of development time. And now, my favorite story. After these changes were implemented, after we had the snapshots of feature available in data warehouse, a product manager came to 2 of our data scientists and asked, can we predict if this user is a business user, which means that company pays for their trips? And they said, yeah, we'll take a look into that. They just downloaded some part of the data from the feature store, like 100-something features, deleted some of the features they didn't care about, plug them into their kind of daily go-to model for the first prototypes. And in under 2 hours, the guys were able to build a proof of concept with pretty good accuracy just from purely existing features. If you can do that, how fast can you do data science? How many more ideas can you try? And how many more ideas you can put to production? I'm really proud that we were able to do that. And I think this is something that we should strive for, to give the tools for our data scientists to do their best with their skills. So from this reality, where we had to spend a lot of time on data collection and building up infrastructure, we came to this new reality. Now we spend a bit less time on data collection. We still invest and build a lot of tools for infrastructure to make experimentation better, to make validation of the data better, and all of that. But overall, we were able to cut down time for a project a lot. And if you can do that, if you can reduce the time it takes to get from idea to production by half, you can do twice as much data science in a year. And also, every next person you hire will also be 2 times more productive. So investing in this kind of projects really, really pays off. So key takeaways. I kind of touched it, but didn't get too deep. But please, find the most impactful problems. As technology people, we like to build and try stuff just because it's interesting to us, and that's great. But sometimes, if you solve the right problem, the returns can be immense. You can get much more things done, and everybody will be happier. A bit related to that, decide what to build and what to buy. To us, making a decision to use something off the shelf, for example, managed technology like Redshift, or using some open source solution like Airflow, was able to save a lot of engineering time to work on the things that actually matter and deliver the products that were actually unique and useful. And inside the company, we always try to follow 20-80 rule. Focus on 20% of things that give you the 80% of result. On one side, you don't get to build perfect thing. That's true. But over the years, you'll be able to build much more super valuable things. And this is something that I think Bolt has been really, really great at. Our team is way smaller than our competitors, but we are able to be more efficient in terms of how we spend resources that we have. And as data science is a scarce resource, we don't have too many data scientists without jobs, wandering on the streets, not being able to get something. Hiring is hard. It's hard to hire engineers. It's hard to hire good data scientists. So making sure that people do what matters is really, really important for success as a company. Next week, I want you to think, how can you make your data science better? I cannot give you answers. I can only ask you a question. What worked for us may be different. You can be at a different stage. You may have different needs. But please think how to make your people happier and more productive. And at Bolt, we are building European leading technology company. We are hiring people across many different roles, engineers, data scientists, product, whatever role you name it. And we have a lot of interesting projects. We just launched food delivery. We launched scooters last year. And recently, we partnered up with the University of Tartu, one of the best universities in Eastern Europe, to work on self-driving project. And there are many more exciting things coming up. So if that sounds interesting to you, check out our careers page and look up at our tech blog. My name is Dennis. I'm from Bolt. Thank you very much, and do great data science.
Okay, so thank you very much, Dennis. Guys, question to you, because we have a 10 minutes break. Do you want to ask questions and take some time from the break, or do you want to go on a break? Questions? Okay.
Right.
So the first question is, how do you calculate your arrival time?
Okay, that's a good question. So do we use Google Maps time or our algorithms? I'll tell you a story. Usually when we enter a market, we use Google Maps because we don't have the data. But we have the proven ability So I mentioned before that we are developing our own maps infrastructure. We have a really great team based in Romania that are working on this maps infrastructure that uses our data. In some cities, especially in Africa, Google Maps are not updated. People are going this way, but on Google Maps there is no road. And with our tools, with our technology, with our knowing the locations of drivers, we're able to build actually maps that are better and give better accuracy on ETAs than Google Maps in some cities. So we try to invest in our own infrastructure because we think this is crucial to business, but we still work with Google Maps. Have you looked at ClickHouse instead of Redshift? It's open source and free. That is true. Open source, free is good. What we saw is that our data engineering team is actually quite small compared to many other companies of our size. So we are a unicorn. We are more than $1 billion company, but there are just a couple of people working on our data warehouse. If we would have to manage and set up machines and do the backups and all of that by ourselves, we wouldn't just have time to work on more impactful projects. So although in future we can try out different technologies, and we are definitely working on alternatives to Redshift for some of the workloads, being able to start fast and get things running without 5 engineers managing machines was a big benefit to us.
What types of models do you use in production? Simple linear regression, decision trees?
So actually, I cannot answer like all of that because we use different models. That's the thing what we care about, that we don't want to tie the hands of our data scientists in using only this technology or make them write only Spark, only models that can be done with Spark machine learning, for example. So we use trees, linear models, neural nets. We use multiple of models, like a tool for a job. And we try to give as much freedom to them, to data scientists, so they can just take the model, train it, deploy to production, their Python container, and I don't personally really care what's inside there.
Okay, and one more question, the last one. Any of your features is available as SQL?
So not every of the features available in SQL, definitely. Many of them are, and of course not all the. So this solution, feature store, explained this is a tool for its job. Sometimes you need fresher data. Sometimes this data is not available in data warehouse yet. So definitely for more real-time use cases, we have to use different approaches. And any of your features available in SQL, as SQL? I still would say mostly yes, because everything that happens inside a company is stored in a database or is in logs, and there is a way to extract this information. Of course, SQL can be like that. It can be joins of 20 tables, but mostly yes.
Okay,
Anything else?
Yeah,
All right.
We
Thank you very much.
Out of time. Thank you.